So basically the idea of this inner solution is, again, we need to rescale our wall normal coordinate. Okay, we need to rescale the wall normal coordinate, and the idea was that so far when we looked at the dimensionless Navier-Stokes equation, so this guy, so here we took both length scales in x and y as L, okay, as some L, and then for large Reynolds number, for Re much greater than 1, we said that, oh, this term should be negligible, and that's how we ended up with the inviscid equations, and we said that that is not the full story. The inviscid solution is only this region. Okay, sometimes you will see this as being called as ideal flow region, or potential flow region also in some textbooks or papers. They are basically referring to the region outside boundary layer where all of this holds. And then we said that this is not the full story. The length scale in y should be different if we want to look at boundary layers. Okay, and the idea here is that the length scale in y should be this some boundary layer thickness at some downstream distance L. Okay, so this usually, which is x equal to 0, y equal to 0 point, this is usually called the leading edge for the obvious reasons. And what we are saying is that after a distance L from the leading edge, at a distance L from the leading edge, what is the boundary layer thickness, and that is our characteristic length scale in the y direction. And so x star is basically still x by L, but y star now is y by delta. Okay, and this is the basic assumption that we use. So just to make clear which length scale was used in this RE, I am going to put a subscript L here, and I am going to highlight that this is REL, which we are assuming is much greater than 1. So with this assumption, we are going to proceed with our analysis, and as I was discussing at the end of last lecture, the idea is that the region, which is this one, okay, this region is where we are interested in when we look at the boundary layer theory. Basically, when your delta is not so large, delta is such that you are still close to the wall, but your L is such that you are far away from the leading edge. Okay, the reason why I am saying this, that L is far away from the leading edge, is to make sure that your REL, which is basically u infinity L by nu. So we want to make sure that we are working in this limit. So I am trying to say that for large L, this quantity will always be much larger than 1, okay, for sufficiently large L, irrespective of the mean stream free stream velocity u infinity and the type of fluid that you are looking at. Okay. So if you are looking at a very viscous fluid which has a very high kinematic viscosity, then you need to look at even further away from leading edge to stay within this regime when REL is much greater than 1, and that is where all of this theory is going to be valid. We are going to use REL much greater than 1 in all of the further derivations. Okay, and some of you might have already guessed that we are going to get this 1 by REL places, and that we will try to ignore those terms. We will try to ignore. Now before we do that, we need some relation of how this delta relates to L. Okay, we need some relation between this delta and L. Okay, you will see why that is required. So let us proceed without having that relation for now, and let us look at our dimensionless continuity equation. So when you non-dimensionalize your continuity equation, you will get u infinity over L del u star over del x star plus some v over delta del v star over del y star. So here I have assumed that this u star is u by u infinity and v star is v by some capital V, okay, where capital V is my length scale of velocity scale in y direction. Okay, capital V is my velocity scale in y direction, and from here we see that del u star over del x star is this v by u infinity times L by delta del v star over del y star. Yeah. Hmm? So here we said that the scale, not dimension, this is for scale, the scale of that is L. We assume both the scales are equal, and that is the assumption we are breaking apart from in boundary layers, where both the scales are not same anymore. Okay, both the scales are not same anymore, because if both the scales are similar, then you are in this regime or in this regime. Okay. Now both the scales are similar holds for both of these two regimes, but where do you think REL much greater than 1 will hold, here or here? In, let's say this is regime 1, regime 2, in which one will REL much greater than 1 hold? 2, right? Because if you're very close to the leading edge, L is small, so you cannot be sure if your REL is much greater than 1. Okay, so naturally the inviscid flow approximation also holds for region 2 only, region 1 and let's call this region 4, and the we are trying to analyze region 3. Region 1 and region 4 are basically untouched by our boundary layer theory. Okay, some of you may be able to argue very easily that region 1 is basically where your Reynolds number is moderate, so you cannot do any simplification to your governing equation, you got to solve the whole Navier-Stokes equation. Okay, in your region 4 you may be able to say that y length scale is very large, x length scale is not so large, and you may be able to do some approximations here. Okay, but we are not going to bother about those approximations, we are primarily concerned about region 3. So now getting back to our continuity equation, dimensionless continuity equation, we again see something very similar to what we had in our lubrication approximation. So we have this v by u infinity L by delta appearing here. Now again, since your delta is changing, so your delta here is this, your delta here is this, so you see a change in x direction velocity as you move further downstream. You see this change in x direction velocity as you move further downstream. Okay, this change is going to be very small, but there is a change. So if there is a change in x direction velocity further downstream, there is a del v by del y. If del u by del x is non-zero, del v by del y is also non-zero, no matter how small. Okay, we are not bothered about how small these quantities are. We are saying that x direction velocity changes, or you can also look at it like this, that x direction velocity just right next to the leading edge is basically 0, or let's say, let's look at here, x direction velocity here is u infinity, and as we move away from the leading edge, as we keep moving away from leading edge, the x direction velocity will keep getting smaller and smaller. Okay, because you are going to keep moving inside, further inside the boundary layer. The boundary layer is actually growing. Okay, the effect of boundary layer is growing. And so the idea is that the only reason why you have a y direction velocity is because you have a change of u infinity by L over a length scale. You have a change of u infinity over a length scale L, and we say that is equal to this. So from here again we get that v is basically u infinity delta over L. You can argue it the other way also, that you have a y direction velocity because you have a change of this delta in x direction. Okay, you have a change of this delta in x direction, so it is very much similar to your wall shape changing in x direction slowly, as we had in our lubrication theory discussion. And so there also we said that V is basically change in y over change in x times u infinity, and so we get that, and basically V by u infinity times L by delta becomes 1. So our continuity equation remains as it is. Now let us look at our y momentum equation. Before we look at y momentum equation, we have to choose a pressure scale, okay, because in your momentum equation you will have pressure scales. Now in lubrication theory we had pressure scale which came from viscous stresses, okay. If you recall, lubrication theory was a problem, was dealing with problems like this. Both of these are walls and you have flow that is either driven by pressure or you have a flow that is driven by movement of the walls, okay. If you recall, inertia was primarily negligible in our lubrication theory. It was the flow boundaries or domain boundaries that were driving the flow. Here you have the flow's inertia that is driving the flow, okay. You have a flow that is grazing past this flat plate and you have a boundary layer forming because the boundary layer is sort of some fluid that is being dragged by your free stream flow, okay, and you have a plate that is trying to hold it back and you have a free stream that is driving the flow. So there is flow's inertia that is driving flow inside the boundary layer. So inertial scales are not negligible in your boundary layer, and that is the primary difference between boundary layer and your lubrication theory. A lot of it looks like same, looks like lubrication theory. You have a y length scale and you will see in a moment that this y length scale is smaller than x length scale, but there is a primary difference between boundary layer theory and lubrication theory, and that is inertia is not negligible now. It's the inertia that is driving the flow. There are no boundaries that are moving. The flow domain boundaries are not moving which are causing the flow, it's the inertia that is causing the flow. So if inertia is causing the flow, then a suitable pressure scale is actually this guy, okay. So we make the Euler number 1 basically, and pressure scale is this, and now we look at the y momentum equation. So let us non-dimensionalize y momentum equation. We are looking at steady boundary layers, okay. We are looking at steady, and as I was discussing yesterday, there is no mathematical equivalent of this assumption, but we are looking at laminar boundary layers, okay. So I am going to drop the unsteady term everywhere. So let us non-dimensionalize our y momentum equation without the unsteady term. So we will get v square over delta v star del v star by del y star plus u infinity v over L u star del v star over del x star equals minus. So the pressure scale is rho u infinity square. So we have a rho u infinity square over delta del p star over del y star plus now we have viscosity times, let's say, capital V over, let's take delta square, then we will have delta over L whole square del 2 V star over del x star square plus del 2 V star over del y star square. Okay, this is our non-dimensionalized y momentum equation. Let us try to simplify it using this relation. So v square by delta, what do we get? So v square by delta is what from here? You have u infinity square delta over L square. Okay, so we get u infinity square delta over L square. Same from here, when you substitute v as u infinity delta over L, you will get the same thing from here. So we can write v star del v star over del y star plus u star del v star over del x star. Here we have minus rho u infinity square. Oh, there was a 1 by rho also that needs to come here, and so that will cancel out. So rho will go away. So you have a minus u infinity square over delta del p star over del y star. And then what do we have here? Let's keep the same thing. We'll substitute for v. So nu u infinity by del by L into delta. Now we have delta over L whole square. Okay. So let us divide this whole equation by u infinity square by delta. Okay. We are dividing the whole equation by u infinity square by delta. So what will we get here? We will get delta over L whole square times this nonlinear term minus del p star over del y star. Okay. And so we have divided by u infinity square by delta. So we will have some delta by u infinity square. So this will become nu by u infinity L. And then we will have del 2 v star by del y star square plus the square. Okay. So this is the equation that we get. Let's not make any assumptions so far. Let us just see that this nu by u infinity L is what? What is this nu by u infinity L? 1 by REL simply. So let's just replace this and not make any further assumptions as of now. Okay. Before making any assumptions, let's look at x momentum equation as well. So let us non-dimensionalize the same way. Let us look at x momentum equation and we'll get u infinity square over L u star del u star over del x star. You can show that you will get the same coefficient in front of the other term when you non-dimensionalize. Okay, because you will have a v coming and then you will have a v by delta which is same as u infinity over L. So you can get the same term here and then we will have minus rho u infinity square over rho del p star over del x star L and then a plus nu u infinity over L square and then we will have actually yeah, let's write delta square here and then we will have delta over L whole square del 2 u star over del x star square plus del 2 u star. Okay, so let us divide this whole equation by u infinity square by L. Rho cancels out here, so we will get u star del u star over del x star plus v star del u star over del y star equals minus del p star over del x star. And now what do we get here? So we'll have a nu by u infinity delta square and then L. So I can write that nu by u infinity L and then an L by delta square and then the terms inside are as it is. So let us not make any assumptions as of yet also just recognize that this nu by u infinity L is essentially 1 by REL. Okay, and now is the time when we want to have a relation between this delta and L because otherwise we cannot make any assumptions. Yes, we can say 1 by REL is much smaller than 1, but that is pretty much it. We do not know how this delta by L behaves. Okay, but we can get a relation between delta and L by using some physical reasoning and the reasoning goes something like this. So let us say you have this flat plate and you have this boundary layer that is forming and let us track a fluid particle here. Okay, let us track a fluid particle here that is traveling with the speed of u infinity in the x direction. Okay, in what time will it travel the distance L approximately? What is the time scale in which it travels the distance L? that is basically L by u infinity, right? That is the time scale in which this fluid particle travels the distance L. Now, for this particle to start feeling the effects of plate, for this particle to start feeling the effects of plate, basically there is this momentum deficit on this plate. So, you have momentum deficit on this plate, deficit meaning that here the momentum is rho u infinity and here it is 0, and as you move further downstream this momentum deficit is actually diffusing up in the y direction. So, if you have a camera, let us say you have a camera and you are visualizing this particle, and let us say you are traveling, your camera is also moving with u infinity, then you what you will see is you will see that the effect of momentum deficit, which is basically momentum deficit is maximum at the plate and that deficit is diffusing upwards. It is very same as what the problem we had for an impulsively moving plate. There you had momentum, non momentum deficit that was diffusing. The plate moved impulsively in the direction x and there was a momentum that the plate had, and that momentum started to diffuse up due to kinematic viscosity. Here it is the opposite of that. You have momentum that you have up in the free stream and you have a deficit at the plate, and that is diffusing upstream, that is diffusing up from the plate, but not in time, but in the downstream direction as the particle moves. Okay, this diffusion, if you keep tracking the particle, you will see that this diffusion actually makes the deficit diffuse upward. Okay. So, in time tau L by u infinity, which is given by this L by u infinity, you will start feeling, the particle will start feeling the effect of plate if the particle has a y length delta, which is given by what? If this delta is given by this nu times tau. Okay. Basically, if the particle is delta away from the plate, then in time tau it will start feeling the effect of the plate. Okay. In time tau it will start feeling the effect of the plate. That is how we reasoned the momentum diffusion due to impulsively moving plate, that after time tau the effect of moving plate is felt in the fluid at a length scale square root nu tau. Okay. That let us say you have this impulsively moving plate at time t equal to 0, you have this as the velocity, it is 0 everywhere and it is some u infinity here, and after some time tau you start feeling the effect, you start feeling the effect at length square root nu tau. Yeah.
Say that whichever part of the fluid feels the effect of the plate, in this case, is that part of the boundary layer?
Yeah, that is.
So then, boundary layer is not like, I mean, I might it's like a thin region.
Yeah.
And by this definition, there is no limit to the boundary.
Yeah, of course, for x tends to infinity, the boundary layer will be of infinite thickness. That is the whole point, that here also for t tends to infinity, the effect of plate was felt all the way till y tends to infinity. It is the same reason as here, that if you have a plate that is infinitely long in x, then boundary layer will be all over the domain. Okay. It is thin for finite plates. That is the whole point, and you do not have infinite plates anyway. So, if you recall this, then after time t or after time tau, the effect of this impulsively moving plate was felt at delta, which was square root nu tau. So, the effect of this momentum deficit is felt by this particle only if it has a, if it is at a y location of delta or smaller. Okay. So, that means this delta is square root of nu L by u infinity, which means delta over L is square root of nu by u infinity L, or delta by L is simply.
This relation, this square root relation we have taken from the impulsively moving plate.
Yeah, That is where we saw this, that the characteristic length till which diffusion is felt after time tau is square root nu tau. Okay, and this is, I mean, for you guys probably, I mean, I don't want to be very discouraging, but if you have any diffusion diffusion phenomena, that is how the effect of diffusion felt, that is the length over which diffusion effect is felt after time tau. Because if you think about it, it's like a dimensional scaling. Okay, you have a length scale that you want to find out, which is dependent on the kinematic viscosity or diffusivity and time. The only way you can form a length scale is by multiplying the diffusivity with time and taking a square root, because the units of all diffusivities will be meter square per second. How do I say that? If you have any quantity, let us say phi, that is diffusing, you have something, this is your diffusion equation. Okay, the only way this equation makes sense or it's physically relevant if it's this coefficient that you have has limits of meter square per second, and it is independent of what quantity you are looking at. It could be diffusivity of concentration, diffusivity of temperature, diffusivity of velocity, whatever. Any diffusivity has units of meter square per second. Nu is just diffusivity of momentum. So after time tau, the effect of diffusion is felt at a length scale of square root nu tau. Okay, and that's how we get this relation between delta and L. Delta by L is 1 by square root REL. Okay, and now we can make a lot of simplifications, because as you see, this delta by L square we had, this is nothing but 1 by REL. You have 1 by REL here as well, and this delta by L whole square inside also that we have, this is 1 by REL. Similarly, when you look at this equation, 1 by REL times L by delta whole square, what is that? 1. This is 1. Okay, L by delta whole square is REL basically. So this is 1, and then this is 1 by REL. And now we are in a state of using this REL much greater than 1 assumption and writing our leading order equations, because we have already done the rescaling. Okay, we have rescaled the y normal coordinate, wall normal coordinate by this delta, and we have found how this delta relates to the smallness parameter in our equations. The smallness parameter was 1 by REL. Okay, the smallness parameter was 1 by REL. So we can write that this 1 by REL is essentially equal to, if we write this as epsilon square, then delta by L is basically epsilon. So we have done the rescaling. We have done the rescaling of our wall normal coordinate by this delta, which is essentially epsilon times L, where epsilon is 1 by square root REL. Okay, so we have found a relation between this rescaled coordinate, rescaled length scale, the delta, and epsilon, and so we are in a state of writing the inner solution equations. Yeah, I want to. So let us write down the inner layer equations, and let us use this epsilon square for 1 by REL wherever we see. So the y momentum equation basically becomes epsilon square times the inertial terms minus del p star over del y star plus epsilon square times the viscous terms. So that means at leading order, what does y momentum equation give? Hmm? What does y momentum equation give at leading order? Basically what we are saying by that equation is that pressure inside the boundary layer as you move perpendicular to the wall doesn't change. The pressure could change in x direction, okay, the pressure could change in x direction, but whatever the pressure is outside the boundary layer, whatever change in pressure is there outside the boundary layer in x direction, that's it, that's the only change in pressure. There's no change in pressure in the y direction inside the boundary layer. So this all happens inside the boundary layer. What is x momentum equation? What do we get from x momentum equation? We'll get u star del u star over del x star plus v star del u star over del y star equals minus. So I can write a full complete derivative here because it's not a function of y, and then this quantity is 1 basically, and then we have plus you have 1 by REL, which is epsilon squared, and from here we see that at leading order the x momentum equation is u star del u star over del x star plus v star del u star over del y star equals minus. So we have already used basically y momentum equation in here. So we have used the information of y momentum equation. The other equation is your continuity equation, and this set of two equations that you see in front of you, these are what are known as boundary layer equations in obviously Cartesian coordinates. How many variables do you see? How many variables do you see in your boundary layer equations? Hmm? We have three variables u, v and p. How many equations do we have? So what's going on? We have two equations, three variables. What happened here? Or is there some other way we can derive this pressure? Is there some other way we can derive pressure? So if you notice, we said that pressure is not changing in the y direction inside boundary layer. Okay, that means P star is same in region 3 as in region 2. P star is same in region 3 as in region 2. Region 3 is where we are looking at, that's boundary layer, and this is region 2. Because del P star by del Y star was 0. So if you have, let's say you're looking at a particular x location, if you move away from the wall, pressure here is all constant and it's equal to whatever pressure you have anywhere inside region 3 at that x location. Or you can say that right outside region 2, if you want to entertain any y direction variation in pressure outside region 3, you can say that right at the end of region 3, whatever pressure is, that's the same as pressure inside region 3, because it doesn't change in y direction. Okay. So from region 3 to region 2, we have only traversed in the y coordinate, and since pressure doesn't change in y coordinate, so we are saying pressure is same in region 3 as in region 2. Okay, at every x location you can do this. Okay, so how do we get the variation of pressure in region 2? Luckily, region 2 is the outer region. Luckily, region 2 is outer region where we have the inviscid flow equations valid. Or if you look at the inviscid flow equations for steady flows, you will see that mod, so in the dimensional form mod u square by 2 plus p by rho is constant in region 2. You can see, you can so mathematically what this means is that p star inside the boundary layer x star comma y star is equal to p star x star y star tends to infinity. That's what I'm trying to say, because pressure is not varying in y star. Okay, because del p star over del y star is 0. Okay, and p star for x star for y star tends to infinity is governed by this equation. So let us non-dimensionalize this again. So we'll find p star. So we'll have a rho u infinity square by rho, which will go away, and so here you will get plus u by u infinity square plus v by u infinity square half equals constant. And our non-dimensionalization for y direction velocity has been this. So we will get p star plus u star square by 2 plus, again we will get a capital V over u infinity square v star square is constant. So capital V by u infinity, if you recall, this is same as delta over L. So that means p star plus u star square by 2 plus delta over L. Delta over L is what? Epsilon. So epsilon square v star square by 2 equals constant. Okay. Now I am going to put a subscript of infinity to highlight that these are not values at any x comma y, these are values for y tends to infinity. Okay. So p star infinity means it's p star u star infinity is u star and v star infinity is
These relations are not only valid at y tends to infinity.
huh?
These relations are not only valid at y tends to infinity.
So okay, so we are not looking at y tends to infinity, we are looking at y star tends to infinity. Okay, there is a difference between the two. Y star tends to infinity means that you're sufficiently far away from the boundary layer. Doesn't necessarily mean that y itself is going to infinity.
These relations are valid.
Which relations are you talking about first?
The ones that we've derived here.
These?
Yes.
But they are valid for y star tends to infinity, right? Because this equation is valid in region 2, which is y star tends to infinity. Region 2 is y star tends to infinity. Perhaps I didn't make that clear. So region 2 is y star tends to infinity. That's what region 2 is, far away from the boundary layer. If you go back to your asymptotic matching lecture, you will see that's how we matched the inner and outer solution. When we took the inner solution's other boundary condition, so the first boundary condition for inner solution was the whatever u equal to 0 at y equal to 0, but what about the other boundary condition? How did we match it? If you go back to your lecture, you will see that we wrote this asymptotic matching condition that u for c tends to infinity, where c was this epsilon y, or sorry, y was this epsilon c. We said that this is equal to, so this is u outer, u inner, this was equal to u outer for y tends to 0. So, we took this c tends to infinity, the rescaled coordinate we sent to infinity, that is our rescaled coordinate, y star is our rescaled coordinate. Okay. You send this rescaled coordinate to infinity to look at anything away from this inner region. So, inner region is sort of like this, it's sort of like a trap where to escape this inner region trap you have to send your coordinate to infinity, any finite value of your rescaled coordinate, and you will find yourself within the inner region. Okay. So, y star tends to infinity is actually your region 2, which is the outer region. And from here we see that from here we see that dp infinity star over dx star is nothing but minus u infinity star du infinity star over dx star at leading order. Okay, which basically means that your pressure, x gradient in pressure, is nothing but this u infinity star d infinity star by dx star. So, you can replace that in your boundary layer equation and write down the equation as, so let me just replace it here for you. So, you can write down this equation as u infinity star
Subscript of the other u on the right side, right?
star only. Oh, it shouldn't be subscript, it should be superscript. You're right. And now someone would ask, okay, how do you find this du infinity star over dx star? Well, you solve for the inviscid flow. You solve for the inviscid flow. What is the inviscid flow past a flat plate? What happens to your u infinity as you move past a flat plate? Does it change? No. Forget about boundary layer. That's what inviscid flow is supposed to do, right? Inviscid flow cannot satisfy the ball boundary condition. All inviscid flow can satisfy is your no penetration boundary condition. And what is that no penetration boundary condition? Okay, V is 0, V is anyway 0 coming from infinity. So, for a flat plate, if you have not imposed any pressure gradient for a flat plate with no imposed pressure gradient, u infinity star is basically 1, right? This is non-dimensional quantity. This is a start quantity, it's a non-dimensional quantity. We have non-dimensionalized it with respect to capital U infinity, and so it remains constant. So, it is 1. So, that means this term basically drops out, and your boundary layer equation even simplifies further. Oh, and we have the continuity equation.
You say no imposed pressure gradient. You have pressure gradient in X ray.
Where?
Not as we've only got that.
So, that is the inviscid solution. Okay. I mean that for the inviscid solution, if you do not have any pressure gradient,
So here we have a pressure gradient. It's just
it's a boundary condition that you impose. Okay, it's a boundary condition that you impose. For example, if I'm asking you to look at boundary layer in, let's say, I am asking you to look at boundary layer in a channel where I am maintaining the flow through this pressure gradient. Let's say here you have P1, you have P2. So there is a pressure gradient. Let's say pressure is increasing in this way. Okay. So through this pressure gradient, I am maintaining a flow. And through this pressure gradient, if I am maintaining the flow, then there will be some increase, there will be some development of boundary layer. This is still a flat plate, but there is an imposed pressure gradient on the top. Okay, if your flat plate is in a uniform, is in a, let's say, is an infinite domain, and you are just sending the flow from infinity upstream, then there is no pressure gradient. But if you're looking at a flat plate, which is a plate inside a channel or something, let's say in a wind tunnel where you have an imposed pressure gradient, basically imposed pressure gradient is maintaining the flow. Okay, you could maintain the flow other ways also. You could basically you don't need to create a pressure gradient to maintain a steady flow always, but if you are using a pressure gradient to maintain the flow, then there's no infinite plate. First of all, I'm never saying that the plate is infinite here. Okay, we are never going to look at an infinite plate. That makes no sense. Everything that we are going to look at in boundary layer is going to be looked at some particular downstream distance. Downstream distance L would be larger than this delta, but it's not infinite. We're not looking at infinite plates. We are interested in the region that is far away from the leading edge, but it doesn't mean that the flat plate is infinite. Okay. Because if things were infinite, then from our current discussion, whenever we look at some infinite plate, then we know that the flow is uniform in that direction. But the flow is not uniform in this in x direction. We're not looking at infinite plates. We are far away from the leading edge, but that's pretty much it. So this is the dimensionless version of these equations. The dimensional version, you can substitute L, delta and everything, and you can derive the dimensional version, and you will see that is simply u del u by del x plus v del u by del y equals nu del 2u over del y square, and the continuity equation remains as it is. What are the boundary conditions that we need? How many boundary conditions do we need? So now we have at least equations that are, we have two equations and two variables u and v. How many boundary conditions do we need? Let's look at this equation only. What boundary conditions do we need? What boundary conditions do we need? Hmm? How many boundary conditions do we need in y? Hmm? One? For which one? U or v? Just look at the order of derivatives. No, you have first order in y for v, so you need one boundary condition in y for v. If second order in y for u, so you need two boundary conditions in y for u. You need one boundary condition in x for u as well, because you have del u by del x. So what are those boundary conditions? First of all, u star at any x star y star equals 0 is what? What is this? 0, no slip. We have v star at x star comma y star equals 0 as what? 0, hard wall. Okay. What about u star for any x star and y star tends to infinity? U infinity for the dimensional one, here it is 1. And what about u star for x star tends to 0 and any y star? Look at this region, region 3, 1. Okay. Now this is a very subtle But an important point, I have not put x star equals 0. I have not put x star equals 0 because this region 3, if you think in terms of this asymptotic matching, it's inner region in y, but it is outer region in x. It is an outer region in x. So you cannot put x star equals 0 boundary condition here. You have to match it by sending x star tends to 0 and you are saying it is equal to 1. Okay, and this will be important when we look at this equation and we say that, oh, there are self similar solutions possible to this equation. Okay, and we'll try to derive that self similar solution or at least the equation, and we'll see the result. So this is an important, subtle but important point. It's not x star equals 0, it's x star tends to 0. Okay. So we'll continue from here on Friday. Sorry, which one? So we have 4, no? We have 1 for v in y, we have 1 for u in x, we have 2 for u in y.